Imagine, for just a second, that you are walking into your bathroom tomorrow morning. You step onto your scale, facing the mirror, and you look down.
Okay.
It reads, say, 150 pounds. Completely normal, right?
Right. Totally normal.
But then, just for fun, you step off, turn exactly 90 degrees to your right, and step back on the scale.
Uh-huh.
Only this time, the scale reads 180 pounds.
Which is, I mean, it sounds completely absurd.
Exactly. You haven't eaten anything. You haven't, put on a heavy show. The only thing that changed is the actual direction you are facing.
Yeah, that violates basically every intuitive sense we have about how the physical world operates.
It sounds like something straight out of a science fiction novel, honestly. Because we're taught from day one that mass is this fixed property. Like a brick is a brick, no matter which way you hold it, no matter how you spin it.
Exactly.
But what if it isn't? What if the very concept of inertia, the resistance of an object to being moved, is not a fixed singular number at all?
Right, what if it's dynamic?
Yeah. What if it's something that changes depending on the direction of your movement? So today's deep dive takes us into a stack of revolutionary and, frankly, pretty controversial theoretical physics papers.
Very controversial.
Yeah, primarily authored by Vrbovsky-Banić and Pavel Vrbovsky. And we aren't going to bore you with all the dense mathematical titles. Instead, we're going to pull out their core world-shaking argument.
Which is that gravity and inertia, as we know them, might actually just be an illusion.
Right. And what's fascinating here is the sheer audacity of what these authors are proposing.
Oh, absolutely. They are attempting to unify localized quantum phenomena with massive, astronomical observations.
All by questioning this one single assumption that physics has held on to for centuries, right? The scalar nature of inertia.
Yeah, because classical physics likes things to be binary and neat. We like mass to be an intrinsic, unchangeable property of matter. It's comforting.
It is.
But when you step into the framework we're exploring today, that entire foundation just gets ripped up and replaced with something deeply, deeply dynamic.
So our mission for you today is to rigorously deconstruct this paradigm-shifting concept. We are going to start incredibly small, like down at the subatomic level.
To understand how magnetic fields might actually be creating this illusion of weight, yeah.
Exactly. And from there, we'll dive into the quantum realm to look at how electrons actually move. Then we're going to build a bridge to the macroscopic world.
Right, exploring how this theory proposes a totally new flat space explanation for the orbit of Mercury.
Which is wild. And even why the sun's atmosphere is mysteriously hotter than its surface. And finally, we'll show how the authors claim this solves a very earthly mystery. Why certain radioactive elements seem to decay faster in January.
It is a massive intellectual journey. And I think we have to be clear up front, we are exploring a theoretical framework here.
Right, important disclaimer.
Yeah, Banić and Vrbovsky are making profound claims that challenge deeply entrenched scientific consensus, especially regarding Einstein's general relativity.
Yeah, we aren't taking sides. Our goal isn't to declare them definitively right or wrong, but just to understand the intricate mechanical logic of their universe.
Exactly. We're just looking at the math and the physical arguments they present.
Okay, let's unpack this.
Right.
Because to understand where we are going, we have to start at the very foundation, which is Vrbovsky's electrodynamic model.
Right.
Standard physics, like the stuff we all learned in high school,
Yeah.
treats mass as this intrinsic scalar property.
Yeah.
You have a bowling ball, it has a certain mass, period.
Yeah, you push it, it moves, you give it kinetic energy.
But Vrbovsky says, wait a minute, let's look at kinetic energy differently. He argues that kinetic energy isn't some abstract, invisible property of a moving body.
Right. Standard textbooks treat kinetic energy almost like a bank account. A particle moves faster, its account goes up.
Right.
But Vrbovsky demands a physical mechanism for that. He argues that kinetic energy is a physical phenomenon completely localized within magnetic fields.
Okay, so let's trace the causality there.
Sure. Imagine a single charged subatomic particle, like an electron or a quark. It's just sitting there at rest.
Okay.
Now, you apply a force to accelerate it. According to this framework, as that charged particle accelerates, it generates a surrounding magnetic field.
Right. Moving charges create magnetic fields. We know that.
Exactly. But creating that field isn't free. Forming that magnetic field actually consumes energy from the vacuum.
So the universe doesn't give out free lunches. If you want a magnetic field, you have to pay for it in energy.
Precisely. And this energy consumption, the literal physical effort required by the particle to build and sustain that magnetic field as it moves, creates a physical resistance to acceleration.
It pushes back.
Yeah, it pushes back against the force you are applying. That resistance, that drag, is what we macroscopically experience as an inertial force. Vrbovsky calls it virtual mass.
Okay, virtual mass. So the energy you transfer to give a body momentum isn't magically disappearing into an abstract concept.
No, it is physically stored in the magnetic field generated by the moving charges within the body.
I'm trying to picture this physically. Is this like dragging a strong magnet through a giant sandbox filled with iron filings?
Oh, that's a really good way to think about it.
Like if the magnet is just sitting there in the sand, it's easy to hold. But the faster you try to drag it through the sand, the larger the cluster of iron filings you gather around it,
Yeah,
right?
right, exactly.
So the more filings that stick to it, the heavier it physically feels to pull.
Yeah.
The resistance isn't the magnet itself, it's the interaction with the sand.
That is a phenomenal analogy, yes.
Yeah.
The faster you move it, the larger the field of iron filings it has to, organize and drag along with it. And that manifests as resistance to your pull.
Wow.
The mass isn't an intrinsic property of the magnet. The mass is the interactive process of dragging the filings.
That is wild. Because if this localized view of kinetic energy holds up, it changes our entire philosophical understanding of momentum and really of reality itself.
It really does.
Because if mass is just a localized field energy state, just the resistance of creating a magnetic field, then the concept of solid matter is largely an illusion, isn't it?
Pretty much, yeah.
Like, a brick isn't heavy because it's full of some magical heavy stuff. It's heavy because it's full of billions of moving quarks that are desperately trying to drag their magnetic iron filings, so to speak, through space whenever you try to push it.
Exactly. It redefines inertia from a passive label to an active, ongoing conversation between a charged particle and the space around it.
Okay, but this raises an important question. What happens when you don't just have one particle, but a system of particles?
Right, because the universe isn't just single, isolated electrons. It's bound systems. Protons, atoms, molecules.
And this is where Banić's development of Vrbovsky's foundation becomes absolutely critical, right? We have to move from single particles to bound states.
We do.
Because if I'm holding that magnet in the sandbox, what happens if I bring a second magnet into the exact same sandbox? Their magnetic fields are going to interact.
Yeah, so let's look at a bound system. Say two charges, Q1 and Q2, separated by a specific distance, which we'll call d.
Okay.
When these two charges are bound together, say they're forming a simple molecule or even just the quarks inside a proton, their individual electrostatic and magnetic fields don't just exist in isolation anymore.
They overlap.
They overlap, they permeate the exact same space, and they undergo spatial interference. The papers evaluate the spatial volume integrals of these overlapping fields.
Which is a pretty heavy calculus, right?
Very heavy calculus. But conceptually, they're just calculating how these two fields add together or cancel each other out in three-dimensional space.
Okay.
And when you do the math on that interference, you get a specific magnetic interference energy. The authors label this equation too in their text, delta Wilm interference.
Okay, so they have a strict equation for how these fields interact. But wait. If these two particles are bound together and they are moving through space, the shape of that overlapping field has to look different depending on which way they are moving.
Right.
Like moving side by side versus moving one in front of the other.
You've just hit the absolute core of the theory. Crucially, this interference energy is not a constant number. It depends directly on the angle which the math calls theta, between the velocity vector of the overall system and the separation vector between the two individual charges.
Wait. Are you saying the overlapping fields change depending on the angle?
I am.
Does that mean if I turn a bound system 90 degrees, its actual physical resistance to movement changes?
Yes, it does.
This is the bathroom scale. This is the exact analogy we started with. If I step on the scale sideways, I weigh something different because the angle of my particles relative to my movement changed.
Well, in a theoretical sense, yes. Though, for a macroscopic object like a human, the trillions of random molecular orientations average out, so you don't actually notice it.
Oh, man.
But at the microscopic level, for an aligned system, it is exactly the bathroom scale. Because the mass defect, the change in mass caused by this overlapping field energy, is direction dependent, which means the bound system's resistance to acceleration is anisotropic. It is literally different in different directions.
Here's where it gets really interesting. How do they express that mathematically? Because, F equals ma isn't going to cut it if it can be three different numbers, depending on how you look at it.
Exactly. To describe this physically and mathematically, the authors argue we have to completely discard the idea of scalar inertia. You can't just use a single number m for mass anymore.
So what do they use?
Instead, they define a symmetric rank 2 inertial mass defect tensor, denoted as me.
A rank 2 tensor. Okay, for anyone whose linear algebra is a bit rusty, let's break that down.
Sure.
Think of a scalar as a single point of data, just one number, like speed, right? And a vector is a number with a direction, like velocity. But a rank 2 tensor is like a matrix. It's a mathematical grid that describes how something behaves dynamically depending on the direction of the input.
That's a great way to describe it. We aren't just dealing with a single block of mass anymore. We are dealing with a directional landscape of mass.
Okay, so how does this tensor actually work in the math?
Well, it maps out the resistance to acceleration in three-dimensional space. When Banić performs a principal components analysis on this mass tensor, which is essentially simplifying the grid to find its core axis, assuming the separation vector between the two charges is aligned along the z-axis, the tensor becomes diagonal.
Okay.
And it reveals a spectacular rigorous inequality. Parallel is strictly less than imperp.
Okay, let me translate that. So in parallel, the mass, when moving parallel to the bond between the particles, is less than imperp, the mass when moving perpendicular to the bond.
Correct.
So if I have a microscopic dumbbell, two tiny weights connected by a rigid bar, and I push it straight along the bar like a spear, it's literally easier to move than if I push it from the side like a snowplow.
You've got it. A bound system is physically lighter when accelerated along its longitudinal bonding axis than when it is accelerated perpendicular to it.
Oh.
Yeah, the source text uses very specific falsifiable phrasing here. They state that, quote, its virtual mass defect is exactly twice as large when accelerated along its longitudinal axis compared to its transverse axis.
Twice as large.
Yes. Because the charges typically have opposite signs in a stable bound state, this magnetic interference energy is negative, meaning it actually reduces the total mass of the system.
Oh, I see.
And it reduces it twice as much when the system is moving along the bond. The spear is lighter than the snowplow.
My brain is doing flips right now.
Yeah.
The dumbbell is actually less massive depending on how I hold it.
Yeah.
But what happens if I push it diagonally? If inertia is different depending on the angle of force, and I apply a force that isn't perfectly lined up with the spear or the snowplow, what happens then?
This leads directly to one of the most spectacular physical predictions of this entire framework. It's called the anomalous transverse drift.
The anomalous transverse drift. Okay.
Because imparallel and imperp scale differently, if you apply a force vector at an arbitrary diagonal angle to that internal bonding axis, the resulting acceleration vector will absolutely not point in the direction of the force.
Wait, it's a wonky shopping cart.
A wonky shopping cart.
Yeah. Imagine pushing a shopping cart with a busted wheel. You push it straight ahead with all your might, but the internal resistance of the system, the busted wheel dragging on the floor, makes it drift sideways.
Oh, right.
The direction of your force does not match the direction of the cart's acceleration. You push north, the cart drifts northeast.
That is a very grounded way to look at it, yeah. The math in the papers outlines this beautifully in equation 14.
What's the equation?
The acceleration vector, A, equals the inverse of the mass tensor, M, multiplied by the force vector, F.
Okay, so the tensor's in the middle of the F and the A.
Exactly. And this is a sharp, fundamental deviation from classical Newtonian physics. Newton assumes AM is a scalar. Push north, accelerate north. But this tensor math says the object itself resists the northern push differently than the eastern push, so the resulting motion is a geometric compromise.
It undergoes an anomalous transverse drift perpendicular to the applied force line. That is incredible.
It really is.
It implies that if you push certain materials, they will seemingly disobey the laws of physics by dodging sideways.
Right, it looks like they're breaking the rules.
But this is all math on paper so far. Anyone can write a matrix that says a dumbbell moves sideways. Do the authors propose a way to actually prove this in a real lab?
They do, and this is where the rigorous nature of the papers really shines. They detail what they call Experiment 2, the anomalous torsion drift test.
Okay, how does that work?
The idea is to construct a macroscopic torsion balance, basically a highly sensitive hanging pendulum that can twist. But you can't just hang a piece of lead on it, because lead is isotropic. Its molecules are jumbled in every direction, so the directional mass differences average out to zero.
Right, like the human on the bathroom scale. You need something where all the microscopic dumbbells are pointing in the exact same direction.
Correct. You need a highly anisotropic test mass. They suggest a single massive crystal of graphite or a parallel-aligned array of carbon nanotubes.
Oh, that's smart.
Yeah, so you hang this perfectly aligned crystal on the torsion balance. Then you apply a highly calibrated electrostatic force at a specific known angle to the plane of that molecular alignment.
And if classical physics is right, the torsion balance just swings straight in the direction of the electrostatic pull, right?
Exactly. But if Banić and Vrbovsky are right, that non-collinear acceleration will cause a measurable anomalous sideways torsion drift. The pendulum will twist sideways in a way that classical physics dictates is absolutely impossible.
Man, I would love to see someone actually build that. And they propose another test too, right? The modulated Cavendish experiment, which, frankly, sounds like something out of a James Bond villain's laboratory.
It kind of does. For that one, you take this microtorsion balance and you symmetrically focus high-intensity, coherent attosecond lasers onto the mass.
Attosecond lasers.
Yes, the attosecond lasers are key because their pulses are so incredibly brief, a billionth of a second.
Wow.
By symmetrically pulsing these lasers on and off F at the exact mechanical resonance frequency of the fiber holding the mass, you are rapidly interacting with the bound electron states.
So you're basically flicking the mass at the exact speed it wants to swing, forcing the system to ring like a bell.
Exactly. It's a highly elegant way to isolate the anisotropic drift effect from random background noise. The lasers induce the drift in a modulated way, building up the swing until it is undeniably measurable.
That is brilliant. Okay, so we've gone from moving quarks to tiny dumbbells to wonky shopping carts to attosecond lasers.
It's a journey.
We've proven, at least theoretically, that this works for large objects like carbon crystals. But the ultimate test of any unified physics theory is whether it survives the weirdness of the quantum realm.
Right, everything gets trickier down there.
Does an electron spinning around a nucleus experience this same directional drag? Let's zoom in on that.
Translating this classical tensor into quantum mechanics is historically where many grand unified theories completely break down. The rules just change down there. To translate a classical concept like our mass tensor into quantum mechanics, you have to replace classical coordinates and momenta with mathematical operators.
Right. In classical physics, a car has a position and a speed. You just measure them.
Yeah.
In quantum mechanics, things are fuzzy. We have probability clouds and wave functions. We use mathematical operators, which are basically complex instructions, to extract observable realities from those wave functions.
Exactly. But there is a massive mathematical hurdle here. This inverse mass tensor operator we've been discussing is a function of spatial coordinates. It depends on r, the separation distance, and the angle between the particles.
Okay.
Because of this, it does not commute with the momentum operator.
Okay, let's translate commute for a second. In basic math, 2 times 3 is the same as 3 times 2, right?
Right.
The order doesn't matter, they commute.
Yeah.
But in quantum mechanics, measuring position and then measuring momentum is not the same as measuring momentum and then measuring position.
Precisely. Heisenberg's uncertainty principle is built on this very non-commutation. If the mass tensor and the momentum operator don't commute, your kinetic energy operator runs the severe risk of becoming non-Hermitian.
Okay, stop right there. You just said non-Hermitian.
Yeah.
I know enough quantum mechanics to know that sounds bad, but let's explain why. What does that actually mean?
In quantum mechanics, operators that represent physical observables, things you can actually measure in a lab, like energy or momentum, they must be Hermitian or self-adjoint. Without getting lost in the matrix algebra, a Hermitian operator mathematically guarantees that its eigenvalues, the actual measurable outcomes, are real numbers.
As opposed to imaginary numbers.
Exactly. If your energy operator is non-Hermitian, you could do all the complex math and end up predicting that a particle has an energy of, say, 5 plus 2i.
Which is impossible.
Right. You cannot have an imaginary energy or an imaginary mass. It makes zero physical sense. It breaks the theory entirely.
So Banić is staring down the barrel of a broken quantum theory here. How does he solve this commutation nightmare and keep the numbers real?
To keep the kinetic energy operator strictly Hermitian, Banić employs what is called a symmetric position-dependent mass, or PDM, kinetic Hamiltonian.
A PDM Hamiltonian. Let's break that down too. A Hamiltonian is essentially the master equation for the total energy of a quantum system, right? The sum of its kinetic and potential energy.
Yes. Banach isolates the anisotropic mass perturbation Hamiltonian within this master equation, and he structures it brilliantly by breaking it down into two distinct terms.
Okay, what are the terms?
The first term is an isotropic, spherically symmetric mass scaling term. It acts on both the radial and angular parts of the electron's wave function equally. It's the baseline.
Okay, got it.
But the second term is where the directional magic happens.
The purely anisotropic radial component.
Exactly. Because the radial momentum, the movement directly toward or away from the nucleus, scales the radial kinetic energy of the electron, this specific term mathematically dictates that the radial mass defect is exactly twice as large as the angular mass defect.
Wait a second. That perfectly mirrors the classical dumbbell we talked about earlier.
Yes, it does.
Moving along the axis versus perpendicular to it, the spear versus the snowplow, the quantum math perfectly matches the classical tensor.
It is a seamless transition across scales, and the implications for atomic structure are profound.
How so?
Well, when Banach applies first-order perturbation theory to hydrogenic states, meaning he uses this new Hamiltonian to calculate the electron orbits in a basic hydrogen atom, this anisotropic mass defect naturally breaks what is known as the accidental Coulomb end degeneracy.
Okay, let's translate that into plain English. Standard quantum mechanics says that certain electron orbits in a hydrogen atom should have the exact same energy level. They are considered degenerate or equal.
Right.
But when physicists actually run highly precise experiments, they find those energy levels actually differ slightly. And standard theory struggles to elegantly explain why without tacking on complicated fixes, right?
Yes, exactly. And what is staggering is the scale at which Banach's framework predicts that difference. The energy expectation value of this mass perturbation scales precisely with the fine structure constant, alpha squared.
Okay, here's where it gets really interesting. For those who don't know, the fine structure constant is this legendary, fundamental, dimensionless number in physics. It's roughly 1/137.
Yep.
And it governs the strength of electromagnetic interactions everywhere in the universe. Finding that your new theoretical framework naturally, without forced tweaking, converges mathematically on the alpha squared scale, which is the exact scale of known relativistic corrections in quantum mechanics, is huge.
It is.
It's that rare moment where the puzzle pieces snap together effortlessly.
It provides immense mathematical credibility to their claims. The authors are mathematically demonstrating that anisotropic mass isn't just a quirky classical idea. It fundamentally underpins the fine structure of atomic spectra.
But wait, we can't just talk about math. Do they have a way to prove this quantum directional mass in a lab? Because we can't exactly hang a single electron from a torsion balance.
No, you can't. But they absolutely have a test for it. They propose the Stark-Zeeman superconducting cavity test.
Okay, let's hear it.
And you are right, in bulk matter, molecules and atoms are oriented randomly. All these directional mass tensors average out to a perfect, boring scalar number.
Right.
So to measure the quantum anisotropy, you have to forcibly break that spherical symmetry. The test proposes taking a beam of atomic hydrogen in its ground state and spin polarizing it.
Spin polarization, meaning you use a magnetic field to force all the atoms in the beam to line up, pointing their quantum axes in the exact same direction.
Yeah.
You're creating a gaseous quantum version of that aligned graphite crystal.
Precisely. You then pass this polarized beam through a high-Q superconducting microwave cavity. By physically rotating the spin axis of the beam relative to the cavity, you change the directional mass orientation relative to the cavity's electromagnetic field.
Okay.
This shifts the vacuum susceptibility. And according to the PDM Hamiltonian solutions we just discussed, this rotation should generate a precise, observable microwave resonance shift of exactly 14.59 megahertz.
14.59 megahertz. That is a highly specific, highly falsifiable prediction.
Very specific.
So if a university builds the superconducting cavity, fires up a spin-polarized beam, and sees that exact frequency shift when they rotate it, they've effectively proven that inertia is a directional tensor at the quantum level.
Exactly. If successfully peer-reviewed and empirically verified, it would fundamentally rewrite quantum electrodynamics.
Wow.
But the papers go even deeper into the quantum mechanics of the atom. They don't just look at the electron's mass. They redefine the nature of the electron's orbit entirely.
Okay, let's unpack this. Because the standard model says an electron is a probability cloud, right? A fuzzy wave of chance surrounding the nucleus. How does this framework view an orbit?
The authors treat the vacuum of space itself as a Bose-Einstein condensate, a BEC. In this model, Bohr orbits are not probability clouds. They are physical, Meissner-shielded standing waves within this BEC vacuum.
A Meissner-shielded standing wave. So instead of a fuzzy cloud of math, the orbit is a literal physical ripple in the fabric of the vacuum, shielded by its own magnetic properties.
Exactly. And this radically changes how we understand a quantum leap.
Oh, interesting.
Classical quantum mechanics says an electron jumps from one energy level to another instantaneously without existing in the space between. It's treated as a literal teleportation, a black box of physics.
Right, the famous quantum leap just pops out of existence here and into existence there.
But Banić and Vrbovsky argue that nature doesn't do instantaneous teleportation. They model the quantum leap as a deterministic, finite time process.
Okay, how does that work?
When an electron drops to a lower energy state, the boundary of its higher orbit standing wave physically dissolves. The wave propagates inward through the BEC vacuum and renucleates at the lower orbital radius.
That is a beautiful image. It's like a caterpillar turning into a butterfly in a chrysalis, rather than just teleporting. It dissolves, travels as a wave, and reforms.
Yes.
But what if the light it gives off? When an electron drops in energy level, it emits a photon.
This is where their anisotropic mass tensor comes back in. The difference in the mass defect between the higher orbit and the lower orbit represents a specific amount of virtual mass energy.
Okay.
When the wave renucleates, that excess mass energy is violently expelled. The emitted photon is not just a glowing particle of light, it is a literal mass defect orbital shockwave rippling out through the BEC vacuum.
A mass defect shockwave. So the atom is literally shedding a piece of its virtual mass, and we see that shed mass as light.
Exactly.
That is a staggeringly physical explanation for something we usually treat as pure abstract math.
It grounds quantum mechanics in physical, fluid-like dynamics.
Yeah.
But to truly grasp the scale of what Banić and Vrbovsky are attempting, we have to leave the subatomic realm. We have to take this concept of mass pulsation and mass defect shockwaves and apply it to the largest structures we know.
So what does this all mean for the big stuff, the cosmos?
Yeah.
Because the sources don't stop at the atom. They take aim at the heavyweight champion of modern physics, Albert Einstein and his general theory of relativity.
They do. If we connect this to the bigger picture, we have to look at planetary orbits. General relativity revolutionized our understanding of gravity. Einstein threw out Newton's idea of gravity as an invisible tether pulling planets together and replaced it with the concept of curved spacetime.
Right, the famous trampoline analogy. You put a heavy bowling ball, the sun, in the middle of a trampoline, and the fabric sags. You roll a marble planet across the trampoline, and it follows the curved fabric, circling the bowling ball.
Exactly.
The planet isn't being pulled, it's just following the straightest path through curved space.
Precisely. And the crown jewel of general relativity, the observation that cemented its acceptance worldwide, was its ability to perfectly predict the anomalous perihelion precession of the planet Mercury.
Right. Let's explain this for the listener. Mercury's orbit isn't a perfect closed circle. It's an ellipse, an oval. And with every single orbit around the sun, that whole oval shifts slightly. It precesses.
Yes.
If you trace its path over decades, it looks like one of those spear graph drawings you make as a kid. Newton's laws of gravity couldn't account for all of this shifting. There was this tiny fraction, about 43 arcseconds per century, that was completely unaccounted for. Astronomers were totally baffled.
Yep, it was a huge mystery.
Then Einstein came along, plugged in his curved spacetime math, and boom, it perfectly predicted that missing 43 arcseconds. It was the ultimate scientific mic drop.
It was arguably the greatest triumph of 20th century physics. But Banić and Vrbovsky are arguing that we don't need curved spacetime to explain this.
Well, time out. Let me push back here. You're telling me a century of astrophysics based on Einstein's curved spacetime might be wrong.
Well,
general relativity is one of the most rigorously tested theories in human history. How can these authors possibly claim that it's an illusion? What is their hard proof that spacetime isn't bending?
to be clear, they aren't saying the math of general relativity doesn't work. They are saying the mechanism is misunderstood. They present a complete, self-consistent model of orbital dynamics in a flat, three-dimensional Euclidean space, no geometric warping, no bowling ball on a trampoline.
Flat space.
Yeah.
Then what is making Mercury do the sparograph?
In this framework, gravity is modeled as a conservative vacuum polarization force. But the absolute linchpin of their argument is that they project the Keplerian coordinates of the planet's orbit onto their symmetric rank 2 mass-defect tensor, the same tensor we used for the microscopic dumbbell.
Okay, let's unpack this for Mercury. How does anisotropic inertia explain the spirograph orbit in flat space?
Think about the shape of Mercury's orbit. As we said, it is highly eccentric. It's a stretched out ellipse.
Right?
As Mercury moves along this eccentric path, the angle theta between its velocity vector, which is the direction it is moving at any given second, and its separation vector, the straight line connecting it to the sun, is continuously oscillating.
Okay.
Sometimes it's moving more tangentially, cutting across the sun's field. Sometimes it's moving more radially, diving toward or away from the sun.
And based on everything we learned earlier with the dumbbells, if that angle theta is changing,
Then the magnetic interference energy is changing, which means the directional mass defect is changing. This forces the effective inertial mass of the orbiting planet to dynamically pulsate over the course of its orbital period.
mass pulsation, you are saying Mercury is literally getting physically heavier and lighter as it orbits the sun, purely depending on its angle of movement.
According to this mathematical framework, yes. The inertial mass of the planet is not a constant scalar, it pulsates. And this variable mass fundamentally alters the momentum conservation of the orbiting body. It generates a non-conservative, phase-shifted self-acceleration vector.
A self-acceleration vector. It's like the planet is creating its own internal thrust and drag. Can we get an analogy for this?
Sure. Think of an ice skater spinning.
Okay, an ice skater spinning on the ice.
When the ice skater pulls her arms in close to her body, moving her mass radially inward, she suddenly spins much faster. She conserves angular momentum.
Right, classic physics demonstration.
In the author's flat space model, as Mercury dives radially toward the sun, its mass defect changes, decreasing its inertial mass along that axis, which acts as a literal forward thrust on the inbound path.
And when Mercury swings around the sun and starts heading back out into deep space.
It's like the ice skater throwing her arms back out. The mass defect shifts again, increasing the inertial mass, which acts as a drag on the outbound path.
Oh, wow.
This mismatch between the constant gravitational pull from the sun and the pulsating thrust and drag inertial mass of the planet creates what the papers call velocity hysteresis.
Hysteresis, meaning a lag or a memory in the system. The planet's mass is slightly out of sync with its position.
Precisely. This velocity hysteresis fundamentally breaks the closed-loop orbital symmetry. The planet doesn't come back to the exact same spot it started. Integrating this hysteresis over a complete orbital period yields a secular precession angle.
Okay, here's where it gets really interesting. When the authors take their flat space, pulsating mass electrodynamic equation, and they plug in Mercury's actual physical parameters, the semi-major axis, the eccentricity of the oval, the orbital period, the mass of the sun, what number do they actually get?
Their calculations yield an exact anomalous precession of 42.98 arcseconds per century.
42.98 arcseconds per century. It is a near-perfect match for the observed astronomical anomaly.
It is.
It mathematically matches a prediction of general relativity. But it achieves the exact same math in a flat space using only electrodynamics and a variable pulsating mass. That is staggering.
It's a rigorous, mathematically sound alternative to space-time curvature. It suggests that the precession we observe through our telescopes isn't the geometry of the universe bending. It is the intrinsic resistance of matter fluctuating as it moves through a field gradient.
But if you have two theories, Einstein's general relativity and Banić's electrodynamic mass pulsation model that give the exact same answer for Mercury, how do we know which one is the true nature of reality? It's a tie.
Well, you have to push the theories to their extreme physical limits to see where their mathematical predictions finally diverge. The authors outline a high eccentricity divergence test for galactic center S-stars.
S-stars. These are the stars orbiting Sagittarius A star, the supermassive black hole at the very center of our Milky Way galaxy.
That's right.
They have incredibly eccentric, stretched-out orbits, and because the black hole is so massive, they whip around it at relativistic speeds.
Yes, because the eccentricity is so high and the speeds are so massive, the angle theta is oscillating wildly. The mass pulsation effect would be massively amplified compared to Mercury.
Okay, so that's the test.
Exactly. By observing the precession of these S-stars over decades, astrophysicists could theoretically measure the scaling ratio and determine whether the orbit follows the geometric curvature predictions of general relativity or the velocity-dependent mass pulsation hysteresis of this new framework. It provides a clear astronomical battleground to test the theory.
But the authors don't just stop at gravity and orbits. They apply this mass pulsation mysteries in astronomy. Coronal heating.
Yes. Postulate 60 in the papers addresses the solar corona. This is a brilliant application of their mass-defect shockwave concept, scaling it up from a single atom to an entire star.
For context, the coronal heating problem has driven astronomers crazy for decades. The surface of the sun is hot, about 10,000 degrees Fahrenheit, but if you move up into the sun's atmosphere, the corona, the temperature inexplicably spikes to millions of degrees.
It defies classical thermodynamics.
It does. It's like walking away from a campfire and suddenly feeling 1,000 times hotter. Classical physics struggles to explain where that massive energy injection is coming from.
Standard models try to explain it with magnetic reconnection or acoustic waves, but they often fall short of explaining the sheer volume of energy. Banić and Vrbovsky offer a nuclear mass pulsation solution.
So walk us through postulate 60. How does a changing mass heat the corona?
It begins deep in the core of the sun. The gravitational and potential pressure is immense. Under this extreme compression, the nucleons, the protons and neutrons inside the solar plasma, are squeezed tightly together.
Okay, so the dumbbells are being crushed together.
Yes. Because they are compressed, their separation distance decreases, which radically increases their magnetic interference energy. This means they develop a massive virtual mass defect. They are essentially storing vast amounts of potential energy in their compressed magnetic fields.
And as the solar plasma churns and boils, these compressed particles are carried outward toward the surface of the sun and eventually into the corona.
Exactly. And as they travel outward, the intense pressure of the core recedes. The local environment expands. Consequently, the core compressed nucleons are allowed to expand. Their separation distances increase back to normal levels.
And when they expand, that stored magnetic interference energy has to go somewhere, right?
Precisely. They shed their virtual mass energy. The math dictates that they release an energy equal to their change in virtual mass times the speed of light squared. Delta m times c squared.
E equals mc squared in action. The mass actually converts back into pure energy.
And this energy isn't shed gently. It is shed violently as extreme ultraviolet radiation and X-rays.
Wow.
The authors propose that the millions of degrees of heat in the corona is literally the exhaust heat of expanding nucleons shedding their mass defect as they escape the crushing gravity of the solar core.
It's like the quantum leap shockwave we talked about, but happening continuously on a stellar scale. The sun isn't just burning hydrogen, its very particles are breathing in and out, absorbing energy in the core and exhaling it as X-rays in the atmosphere.
It is a stunningly unified mechanism. But it begs one final inevitable question.
Which is?
If the sun's massive potential field is capable of compressing nucleons and changing their mass, what does that mean for us down here on Earth?
Right. We aren't Mercury and we aren't S-stars orbiting a black hole. Does this mass pulsation affect anything closer to home?
The authors argue that it profoundly affects everything on Earth, down to the very atoms in your body. And this brings us to the final and perhaps most controversial pillar of these papers: seasonal radioactive decay anomalies.
Okay, I have read a little bit about this over the years, and it usually gets treated as fringe science by the mainstream. The standard model of particle physics says that radioactive decay is completely random and mathematically constant.
True.
A half-life is a half-life. It doesn't matter if you put a radioactive isotope in a freezer, an oven, a vacuum, or shoot it into deep space, it is supposed to decay at the exact same rate.
That is the textbook consensus. However, for decades, various respected nuclear laboratories worldwide have reported real, observable fluctuations in the decay rates of certain radioactive isotopes, specifically things like silicon-32, radium-226, and tritium.
And these fluctuations aren't random noise.
No, they are periodic, they are annual, they peak and trough with the changing of the seasons.
Which classical physics says is impossible. The Earth's seasons, a bit of snow, or some summer heat shouldn't have any effect on the weak nuclear force operating inside the nucleus of an atom. So how does Banić's framework explain this?
We have to connect the earthly laboratory observation back to the astronomical mass pulsation we just discussed with Mercury. Just like Mercury, the Earth orbits the sun in an eccentric elliptical orbit.
Right. We aren't in a perfect circle. Sometimes we are slightly closer to the sun, sometimes we are slightly further away.
In early January, the Earth reaches perihelion, its absolute closest approach to the sun during the year. At this point, the solar gravitational and vacuum potential that the Earth is sitting in is maximized.
We are sitting deep in the sun's field.
According to the unified electrogravitational framework presented in the papers, this intense potential field gradient causes the subatomic boundaries in all terrestrial matter to experience maximum compression.
Wait, You were saying the actual particles inside us and inside a chunk of silicon-32 sitting in a lab are being physically squeezed by our proximity to the sun.
Yes. Just like the nucleons in the solar core, but on a much smaller scale. And here is the crucial mechanical detail. Because of the absolute charge disparity between the particles, the neutron being neutral and the proton being positive, they respond differently to this field.
Okay.
Under this specific solar potential, the neutron compresses more than the proton.
Okay, let's unpack this. If the neutron compresses more than the proton, the delicate architecture of the nucleus changes. What happens to the energy?
It modulates what is called the Q value of nuclear beta decay. The Q value is essentially the total energy released in a nuclear reaction. It is derived directly from the mass difference between the parent nucleus and the daughter products. If the masses and structures of the neutron and proton shift even infinitesimally due to this solar compression, the total energy available for the Q value shifts.
So the mass pulsation from our orbit is slightly changing the energy math inside the nucleus. But wait, I have to push back here. Even if the sun is squeezing the Earth's atoms, the mass defect of this would be incredibly tiny, right? Just a fraction of a percent.
Very tiny, yes.
How could a microscopic shift in the Q value possibly cause macroscopic, easily observable changes in laboratory decay rates that scientists are arguing over?
That is the genius of applying Sargent's law to the problem. Sargent's law is an established rule in nuclear physics which states that the decay constant of a low Q beta emitter scales with the fifth power of the Q value.
The fifth power. So the Q value times itself, times itself, times itself, times itself. That is exponential.
Exactly. Banić explains that this fifth power exponent acts as a massive quantum amplifier. A tiny, almost imperceptible mass energy shift, a fractional electrodynamic mass pulsation caused by the sun, is amplified by 5 times in the decay mathematics.
Let me make sure I understand the physics of why Sargent's law works that way. Why does a tiny change amplify so much?
In beta decay, an atom emits an electron and an antineutrino. These particles have to share the Q value energy, the physics governing how many possible energy states these emitted particles can occupy the phase space scales extremely rapidly as the available energy increases.
Okay, I follow.
If you give the system just a tiny bit more Q value, the number of ways the particles can share that energy explodes exponentially, which drastically increases the probability of the decay happening in any given second.
It's like a microscopic whisper being blasted through a stadium sound system. The tiny gravitational squeeze from the sun is the whisper, and Sargent's law is the amplifier.
Precisely. That tiny 10 to the power of -5 shift in the Q value is amplified into a highly visible seasonal fluctuation that we can track globally.
And the timeline aligns perfectly, doesn't it?
Perfectly. The Earth is at perihelion maximum compression in January. And globally, the observed radioactive decay rates of these specific low Q beta emitters reach their absolute maximum in early January, and they drop to their absolute minimum in July when we are at aphelion furthest from the sun.
So what does this all mean? It means that every January, as you are shivering in the winter cold, shoveling your driveway or driving to work, the very atoms inside your body, the neutrons and protons, are experiencing a localized mass pulsation.
Yes.
They are literally being squeezed by your proximity to the sun, shifting their internal mass geometry. And we can prove it by watching a chunk of silicon-32 decay slightly faster in a laboratory. We are physically, quantum mechanically breathing with the orbit of our planet.
The authors argue it is empirical proof of dynamic mass pulsation, bridging the gap between solar system mechanics and nuclear physics. It ties the macro to the micro in a beautifully seamless way.
This has been an absolutely staggering journey. Let's do a quick recap to thread the needle on everything we've covered today, because we went from the smallest things in the universe to the largest.
We covered a lot of ground.
We started with Vrbovsky throwing out the idea of static, boring mass, arguing that kinetic energy and inertia are just the physical resistance of creating magnetic fields as the charged particle moves. The magnet in the sandbox.
Which logically led to the tensor mathematics of bound systems, proving that overlapping fields create an anisotropic mass defect. A system is physically lighter along its longitudinal axis. M parallel is less than M perp. The spear is lighter than the snowplow.
Which creates that wonky shopping cart effect, the anomalous transverse drift.
Yeah.
When you push a bound system at an angle, something the authors mathematically propose we can prove with attosecond lasers and torsion balances.
Right.
Then we translated that exact same directional mass tensor into the quantum realm with the position-dependent mass Hamiltonian.
showing that the radial mass defect breaks Coulomb degeneracy at the exact scale of the fine structure constant. Furthermore, we explored how Bohr orbits aren't probability crowds, but physical, Meissner-shielded standing waves.
Yeah.
And a quantum leap is a deterministic process of dissolving and renucleating, emitting a photon that is a literal mass defect shockwave.
Yeah.
All of this sets up the 14.59 megahertz Stark-Zeeman cavity test for empirical proof.
And from there, we zoomed out to the cosmos. We saw how this direction-dependent mass means a planet in an elliptical orbit like Mercury is constantly changing its effective mass, creating a thrust and drag velocity hysteresis that perfectly replicates general relativity's 42.98 arcsecond precession, but in completely flat space.
We then applied that mass pulsation to the sun itself, where core-compressed nucleons expand in the corona, shedding their virtual mass energy as X-rays to solve the coronal heating mystery. And we concluded with the earthly proof, the January perihelion causing maximum subatomic compression on Earth, changing the Q value of beta decay and being massively amplified by Sargent's fifth power law into the seasonal radioactive decay anomalies we observe in labs.
It is a single, incredibly elegant framework that attempts to unify quantum subatomic phenomena with macroscopic astrophysics and laboratory anomalies, all by simply abandoning the deeply ingrained assumption that mass is a fixed scalar number.
It challenges us to view reality not as a collection of solid, unchanging objects moving through an empty void, but as a dynamic, interactive web of field resistances. It insists that the universe is an active participant in every movement you make.
It's mind-blowing. And before we go, I want to leave you, the listener, with one final provocative thought to mull over.
Let's hear it.
If mass and inertia are truly just the interactive resistance of overlapping magnetic fields and separation distances, what does that mean for the expanding universe? We know that space itself is stretching. As the cosmic voids grow larger and the distance between bound systems stretches across billions of light years, does the fundamental weight of the universe's matter slowly change?
Wow.
If inertia is essentially a conversation between fields, what happens when the universe gets too vast for those fields to talk to each other? Does matter become fundamentally lighter or lose its inertia entirely as the cosmos pulls apart into the infinite?
It raises profound questions about the long-term evolution of cosmology and whether the fundamental laws of physics are actually changing over deep cosmic time as the geometry of the universe expands.
It really does. It makes you look at the stars and the scale in your bathroom a little differently. Keep questioning the fundamental nature of the reality around you. Thank you for joining us in this deep dive into the sources. Until next time.